Hopefully we're online again. So another brief, this one even more brief, presentation just showing input gain graphs. And so here we've got a graph with the x-axis showing input, the y-axis showing gain. And of course, what that means is your more familiar input-output graph, which we just did an example of previously in the previous video. Gain is just your input minus your output minus your input. That is your gain, essentially. So they're the same graph, basically, but just shown in a slightly different way. But it does mean that compression, expansion, and linear sections and output compression look slightly different on these type of graphs. So how different? How so? Well, let's start with a simple graph just showing a linear section and a hearing aid that then subsequently goes into compression. And then after that compression section goes into an output compression, a very strong output compression. So how would we show that? So the first thing to think when we're doing this is just say to yourself, okay, well, what happens with in a linear section? So as the input changes, what happens to the gain? In a linear section, as the input goes up, the gain remains the same. So the gain, wherever we set it, let's say we'll call it 30 or something like that. As the input goes up, the gain remains the same. It looks totally horizontal here. Let's just put in 30 dB of gain there we're giving for this particular hearing aid. Now, next we've got a section which has compression, right? Just a standard input compression, sort of like a 2-to-1 compression, something like that. So from some point, let's call it, that's my pencil, let's call it at 60 dB. Let's say the hearing aid goes into compression, 2-to-1 compression. So then we're going to have a section, and we'll ask ourselves again, what happens to gain as we increase input in a compression section? As we increase the input, the gain reduces, goes down. So we've got to have a line taking a downward slope. And then at some point, the hearing aid's going to go into output compression. At that point, what's happening as we increase the input? As we increase the input, the gain is going down really dramatically, right? So from that point, it would be, and quickly we'll approach 0. Should have drawn my line a bit longer, shouldn't I? There you go. And we'll quickly approximate 0 dB gain at some point fairly nearby in the input scale. So here we would have had, this might be, now you have to be a little bit careful here because we're showing the output compression point on an input graph. And so this will be correct only for one volume control setting. But let's say at about 95 dB input, it's going into compression. Okay, so that's the basic parts of an input-output graph. Input gain graph. Let's just go back. Back. Let's draw in now a slightly different one. Let's say we have a hearing aid which begins with an expansion section. Okay, so below 30 dB input, we have an expansion section. So what happens in an expansion section? As input increases, gain increases. It's that weird thing, which is the opposite of compression. So as input increases here, we've got to have gain increasing. And we'll say it's going to increase up to some point there, something like that. All right, now notice that that looks like in an input-output graph, we would say that's a linear section, but here we're looking at gain. So that is actually an expansion section. As input increases, gain is increasing. Then the hearing aid has a linear section above 30, which goes along to, let's say, 60 dB of input. Remember our linear section, as input increases, gain remains the same. And then above 60 dB input, we have a compression section, an input compression section. And that runs from 60 all the way to, let's say, I don't know, 90, something like that. Or let's say 100. There we go. And then we have an output compression section again. Okay, which is just a more severe compression, basically. Now you could be asked, I guess, to show the compression ratios here, and to work out what that would look like. Obviously, then you're going to have to put in the gain levels, so the different gain points here. So let's say that's 30 again. So that point there is 30, but then the gain reduces up here during compression. If we said 2-to-1 compression, you're going to have to do some calculations to work out what this gain should be here, right? Oops, what that gain should be there. Because you can't work it out just by, saying 2-to-1, or what does that mean? Well, you'd have to work out the change in inputs, change in outputs. So in this case, for instance, we've got a change in input of 40. So to get a 2-to-1 compression ratio between 60 and 100 for this section here, change in input of 40, change in output, what's the change in output going to have to be to make that 2-to-1? Change in output's going to have to be 20, right? That will make it 2-to-1. So to get a 20 dB, to get a 20 dB change in output for a 40 dB change in input, we're going to have to work out, well, what were our inputs and what was our input to start off with, right? So our input to start off with was 60 plus 30. That was our initial input. It was 90, 60 plus 30. Yeah. So that's our initial output for a 60 dB input. And so then we're going to have a change in output of 20. So 100 dB input will have to have also, so a change in output of 20, that's going to have to be 110, right? That's a 20 dB change in output. So what's our gain going to have to be then? To get a 110 here, it'll have to be 10. So our gain for 100 is 10. And let's just check ourselves to make sure we did that right. So change in input is 40 here. That's simple to calculate because we've got two figures there. The change in output is going to have to be 20 to get 2-to-1. So let's check if we've actually got that. 60 plus 30 is 90. 100 plus 10 is 110. 90 to 110, that's 20 dB. 40 to 20, which equals 2-to-1. And we're done. Okay, but I haven't seen that question in previous exams, but that certainly could be asked of you to have something like that. And you can do it, but it just requires that extra step that you have to do in your input-output graph to calculate the compression ratios. Okay, let's wipe this clean. Just use the eraser there. Okay, and this is very unprofessional. Where's my eraser? Okay, so now what we might just briefly look at is, I'm just going to finish. Somebody asked for, input compression, was it? No, sorry, they asked for not frequency gain, it was output frequency, that's it. So let's change all this just very briefly to finish up. So here, frequency. And this here, if we make that output, now when would we see a graph like that? Not very often, actually. But frequency output graphs are used to show, or usually used to show, the OSPL 90 of the hearing aid. So what does one of them look like? Okay. I mean, you're used to looking at frequency gain graphs, aren't you? I mean, again, if you know the input, then a frequency output graph you can calculate. It's fairly straightforward, relatively straightforward. But let's imagine so it's used usually to show an OSPL 90. So an OSPL 90 might be something, might look something like that or something like that. We fall off in the high frequencies and fall off in the low frequencies. So that's an OSPL 90 graph. So that little, because each line here denotes an input, you could show, that'd be a common thing you'd show on this type of graph, but you could also show a, let's put the numbers in here before we do that. Let's say that's 130 or something, and that's 140. This is a very powerful hearing aid, obviously. Right, so the 90 dB input is giving between 130 and 140 dB output across the frequency range. But you could also show, and then you could, of course, work, could figure that into how much gain is being delivered for a 90 dB input between 40 and, that's very high, isn't it? Shouldn't have done those so high. But anyway, you get the idea. You could do the same thing. You could show output across frequency range for a 60 dB input as well, of course. And, so let's put it in a different color. Again, I don't think you'd be asked to do this very often, but you could do it. So let's say, so the frequency, let's put 60 dB, the output here. Maybe it's a hearing loss, which has got a bit more, bit of a high frequency drop. And then the output could be between, I don't know, let's say, so this is you have to denote, of course, the input level. So let's say that's 65, something like that. Then the output might be between, here in the low frequencies, we might only be giving 20 dB of, sorry, let's call that 20 dB of gain, so that would be, 85. Come back. Okay, 85, and then at the peak up here, we're providing 20, let's say. So at 120, sorry, for a 65 dB input in the high frequencies, we're delivering about 60, that's way too much gain. But anyway, you get the idea. I can't imagine how whether you'd be, or why you would be asked to draw one of those in an exam. But I guess you could be. As I say, it's usually only used to show the OSPL 90 on your insertion, on your manufacturer spec sheets and stuff, as measured on the coupler. But if you're doing coupler measures, you might also do output measures for a 65 dB input or something like that. Okay, but it's not particularly useful graph for showing compression. The way you normally show that is on an input-output graph in normal cases. It's easier to see the compression, or a gain input graph perhaps. It's easier to see how the compression and expansion sections work and where they kick in and so on. So that's a output frequency graph, but very unusual to use those in an exam or in general, as I say. All right, please leave your comments, ask questions or request clarifications as needed, and I'll be happy to answer them. Whoa, stop the broadcast.